In this video I'm going to talk about Euler's theorem about Hamiltonian graphs. So first let's recall the definitions. So a Hamiltonian cycle is a cycle in a graph that passes through every vertex in the graph, and so this is a Hamiltonian cycle, and the graph is called Hamiltonian simply if it contains a Hamiltonian cycle, like any, at least one. So now the Euler's theorem, it is essentially a sufficient condition for a graph to be Hamiltonian. So it says that if you have a graph on n vertices where n is greater or equal than 3, then this condition that so if for any pair of non-adjacent vertices u and v, the sum of their degrees is greater or equal than n. So if this holds for any pair of non-adjacent vertices, then this is enough to conclude that G is Hamiltonian. So essentially what this condition means is that the graph has sufficiently many edges, because like the degrees, so like this is a lower bound on the sum of degrees, so like or sufficiently large degrees, like another way to put it. So if the degrees of vertices are sufficiently large, generally speaking, then it must be Hamiltonian. And the precise statement is this. So let's consider a proof. So it is like it is enough to prove the kind of the opposite statement. So like we prove by contradiction, right? So by contradiction. So we suppose that it is not Hamiltonian, and we will prove that at least for one pair of vertices this condition would break. So we suppose, so this is kind of the opposite statement. We suppose that it is not Hamiltonian. Suppose that G is not Hamiltonian, and we need to prove now. We need to prove that there exists such pair of non-adjacent vertices u and v, such that the degree of u plus the degree of v is greater less than n. So so if we prove that, that would be a contradiction. So we suppose that it's not Hamiltonian, then we find such a pair that would break this condition that is in the statement of the theorem. Therefore it would be a contradiction, right? So that's what we are going to prove now. Okay, so first let's notice that if we add additional degrees to if we add additional edges to the graph without making it Hamiltonian, then it doesn't like it doesn't violate anything. So essentially we can consider, so like this equivalent to kind of taking the maximal counterexample to the original theorem, right? So we take maximal by edges counterexample. So like if we take any counterexample and we start to add edges to the graph until we can without making it Hamiltonian. So it is not Hamiltonian, and we add edges until we can until it is still not Hamiltonian. And then like if we prove the statement, if we prove then this statement for the resulting graph, then for the original graph it would still hold, because the degree of vertices when we add edges, it only increases, right? So if we found a pair of vertices for which the sum of these degrees, so a pair of non-adjacent vertices for which the sum of these degrees is less than n, then in the original graph, where there are less edges, the sum would be still less than n, because the degree of each vertex would be less than in the resulting graph. So yeah, so maybe it's not now correct to talk about counterexample, but let's just say that we add edges. So we add edges to the graph until we can without making it Hamiltonian. Making it Hamiltonian, and it is enough to prove, the statement that there exists a pair for the resulting graph with additional edges, and it is enough to prove the statement for the resulting graph with the additional edges. Yeah. So so now let's consider now two non-adjacent vertices. Non-adjacent vertices, let's say U and V, any non-adjacent vertices, and because they're non-adjacent, it means that we cannot add this edge like in this procedure. We cannot add this h without making it Hamiltonian. It means that the addition of this h uv would make it Hamiltonian, right? So there is no h here. So we take, okay, let's write this. So we take any pair of non-adjacent vertices u and v. Because they're non-adjacent, like the addition of this, like by the maximality by edges of the graph that we take, because we already added all the edges that we could without making it Hamiltonian. So the addition of this, the addition of the edge uv would make it Hamiltonian. Right? So, but what does it mean? It means that it means that there is a Hamiltonian path from u to v somewhere that passes through all the vertices, and what it is missing in this path is only the edge from u to v. So because the addition of this edge would make it Hamiltonian, so it would create a Hamiltonian cycle. So it means that there is a Hamiltonian path, not a cycle, but a Hamiltonian path from u to v. From u to v. Okay, so if there is a path, then we consider the following. So we draw it. Let's make a picture another way. So here is the vertex u, here is the vertex v, and there is a path that passes through all vertices. So essentially, graph looks like this. So, and these are all vertices of the graph. So there could be some other edges, like between some vertices, something like this. But we can draw it regardless of what other edges there are. Like we can draw this path from u to v, and that path passes through all vertices of the graph. So now we notice that. So how many vertices are here? So in total we have n vertices. Two vertices u and v are special, so from which we started, and it remains so n minus 2, right? So n minus 2 vertices. So now we notice that for any pair of subsequent vertices from any pair, like let's denote it x and y. Any pair, so for any pair of subsequent on this path, subsequent vertices x and y. So basically we consider the edges, like whether there are edges or not between the vertices u and x. So like I will draw it as a kind of as a like I will draw it as an edge, but we don't know if it's an edge. Like it would be easier to draw. this, this, and this. So between these four possible edges, like, we notice that no, not all of this. Okay, not all of this. Consider only these two. Okay. Yeah. So from x to v and from u to y. So these two possible edges, we notice that the graph cannot contain both of them. So the graph. Okay. So let me just draw it like this. So we don't know if it's an edge. Kind of in a dashed manner. So from u to y and from x to v, these both they cannot both be an edge. Cannot both be edges. They cannot both be edges at the same time. Why? Well, if, like, by contradiction, so suppose they're both edges, then we have a path from u to y, then we go from, so let's draw it like this. We go from u to y, then we go from y to x, but y by one edge. Yeah, no, it's yeah, I was trying to figure out how to construct a Hamiltonian path, but yeah. So we don't go by the edge x, y, x. So first we go from u to y, like here. Then we go from y to v, here. Then we go from v to x, like this. And then we go from x to y. No, not from x to y. Then we go from x to u, right? So let's write it here. So we go from u to y. Then we go by a chain from y to v. So from u to y, then from y to v, like this. So let me highlight this. This. Yeah. So that would be a Hamiltonian path. Right, so first we go by single edge from u to y, then from y to v by a chain, then from v to x by single edge, and then by a chain from x to u. So we started from u and we ended with u. So this would be a Hamiltonian cycle. This would be a Hamiltonian cycle. Yeah, and we at the beginning we supposed that G is not Hamiltonian, right? So this is a contradiction. So this is a contradiction. So a contradiction that proves this statement, that there cannot be both be edges, because if they're both edges from u to y and from x to v, then we find a Hamiltonian cycle. So therefore, from this contradiction, this statement holds. So, but this means that basically we find that there cannot be too many edges between u and v, because for any, so let's draw again. So we have this chain from u to v that passes through all edges, all vertices, and for any subsequent step, for any edge basically in this chain, in this path, you find that both this and this cannot be edges at the same time. So therefore the degree, so what is then the max, the degree of u plus the degree of v, we can limit it from above, bound it from above. So it is at most, so like in total we have here n minus 2 vertices. So right, and n minus 3 edges. So in this path we have n minus 3 edges, and for each of this edge this statement holds. So from u to this end of this edge, and from v to this edge, to this end of this edge, there is at most one edge. So from u to here and from v to here, between these two, there is at most one. So when we consider all of this n minus 3 edges, so the sum of these degrees of u and v is less or equal than n minus 3. So this is when we consider the so the degree is the number of edges incident to u and v, right? So then the number of edges, so let's put it this way. So here are all the other vertices, so here u and v, and here all the other vertices. So from so there are two special edges from U to the next one in this path, and from V to the next one and this to the previous one in this path. So except these two special edges, so all other edges that go from U and V, so there are two special edges here. But for all other edges, for all other edges, we find that the number of them going from U and V, the sum of them is less than or equal than n minus 3 and two special edges, right? So these two special edges to the next vertex in the path, and all other edges we bound from above by this statement. So in total this would be n minus 1. N minus 1, and this is a direct contradiction to the original statement. So like so here we write that we need to find, so basically we proved this statement. We found a pair of non-adjacent vertices U and V such that the sum of their degrees is strictly less than n. Strictly less than n is the same as less or equal than n minus 1. So we proved what we needed to prove. This basically concludes the, well, this gets a contradiction to the original assumption that G is not Hamiltonian. So therefore it is Hamiltonian, and this concludes the proof of the theorem.